Welcome to all right, Biochar Initiatives in Minnesota, hosted by the Minnesota Composting Council. The picture we see at the top here, it didn't. Oh, now it looks like it did. I'm sorry. Technical difficulties. Lauren, it doesn't look like my slides are changing for the audience.
They were.
Oh, are they?
I see. I think so.
Okay, I guess Kylie's view is just wrong here. So apologies there, but we see at the top here a picture of compost on the left and biochar on the right. And there's really fantastic synergies when we combine these two as soil amendments. Biochar has a huge range of uses beyond just soil amendments, but really the big users of biochar, the real bulk markets, eventually are going to be soil amendments as we develop access to the product, and as you'll learn further today, the various research avenues that are being undertaken. For the attendees, you'll all be on mute today, and you can ask questions in the questions tab at any time. I'll be presenting for around half an hour, and then Jim Doughton has about 15 minutes, and then after that, we'll dive into a question and answer panel with Brian Berry and Bridget Ulrich of NRRI and Kurt Spokus with the USDA, who are all researchers on the biochar topic and making very great headway on the topic right here in Minnesota, as we'll find out. So speaking of what's happening here in Minnesota, just since the start of this year really is when a lot of these things I've personally started to learn about. Kind of at the start of the year, I got invited to participate with a literature review project by U of M grad student Sam Hunt. It's based out of Osakis with a Sustainable Farming Association group. They're looking at what should we be doing with biochar, and as they're especially finding out, there's a lot of mixed research, a lot of maybes, a lot of promises that might not get fully fulfilled, but also a lot of very beneficial uses, a lot of very proven benefits, a lot of reasons that we should be making and using biochar, but also some precautions that are necessary, especially for the agricultural side. Carlton Soil Water Conservation District and Great River Greening are both looking at using Oregon kilns, which we'll explore further, to produce biochar on site when doing forestry cleanups. The City of Minneapolis, as Jim will get into, is acquiring a unit from Artichar, and they'll be operational sometime this summer or fall, making biochar right here in Minnesota. And actually, before even they'll be up and running, North Star Lime in Crookston will be making biochar from corn stover. They got a fertilizer production enhancement program grant from the USDA to purchase a unit, and they will be producing biochar and utilizing it on a farm in the Crookston area. David Abazas with the Northeast Clean Energy Resource Team is pursuing multiple projects. University of Minnesota Duluth and NRRI have a bunch of projects going. The St. Anthony Falls Lab, specifically on the stormwater side, is utilizing biochar. The Civil Engineering Department and Bioproducts and Biosystems Engineering Departments have projects going on where they're doing biochar research. And then as Kurt specifically will talk about, USDA and the NRCS have a lot of interest in biochar. And so we're kind of hoping that the webinar today will be a primer for the upcoming June 28th Minnesota Biochar Summit that Jim and young environmental consultants are planning. There will be more information to come on that very soon. And mark your calendars for June 28th, though, as that'll be the big in-person full-day event where we'll really dive into biochar for the full state and how to progress these markets. But biochar is not a new thing. People have been using biochar and charcoal, as it is really, the same terminology applies, have been using that as a soil amendment for thousands of years. There's evidence of terra preta soils going from thousands of years ago in the Amazon that have these thick layers of char build up in the soil that provides it with these fantastic nutrient retaining qualities and makes it much more fertile than the surrounding soils. And even back in Victorian Britain, there are texts going back to the 1840s that describe the use of charcoal as a great manure. In those days, manure just meant any kind of soil amendment. It didn't specifically mean, a waste excrement product. It was a much more general term for anything you're applying to the soil. And in the photo here, we see back in the 1800s, that's just a big, it's literally a pile of sticks that then they're going to light that from the top instead of the bottom. And we'll get more into why that actually matters. But if you light that pile from the top, you'll wind up with a big pile of charcoal at the end. And that's how they were, there they were making charcoal for using in stoves for heating or cooking. But as we'll dive into in depth here, charcoal is also great as a soil amendment and for other uses. So we've kind of thrown around charcoal, biochar here, activated carbon. All of these terms really are interchangeable. Activated carbon tends to be a process that has a lot of energy input. There's usually steam used to activate the carbon, to puff it and expose these pore spaces. But when the pyrolysis process happens in the right way, you can achieve that same thing as activated carbon, just with the right mixture of gases and heat and time and temperature, and in a much more sustainable, carbon negative way, rather than being a huge energy input. You can actually recover heat from this process to use for heating, generating electricity, all kinds of applications. And so that's what's really exciting about biochar, what the big deal is about why it's this green product. Carbon black is also another product in this realm. That typically actually is made from coal, fossil coal, and that's what gets used in our tires, all kinds of other industrial applications where that carbon material is applied. But that can also be derived from any carbon material. It doesn't have to be made from coal. So thanks to Bridget for this slide that she presented just 2 weeks ago now, presented at the St. Anthony Falls lab. But biochar is carbon negative, and it's a bit of a complicated reason as to why. But at the end of the day, you're able to sequester about 50% of that carbon for thousands of years versus almost 100% leaving to CO2 in other processes. So here's kind of another view of that, a little more simplistic here. But in this case, rice, the biomass, when it photosynthesizes, it's the carbon capture in the air. We see all these technologies that are being promoted currently of these direct air capture carbon sequestering devices that personally I think are ridiculous. We've had plants and trees for millions of years that have accumulated carbon and stored it into fossil fuels that are sequestered in the ground, and we can utilize those resources to capture carbon. And then if we manage those byproducts in the right way, the biomass that's generated, we can turn it into 50% carbon for the next 1,000 years. That's permanently stored, that has great benefits for construction materials and for soil health. And if you're interested in buying credits for these processes, there's currently a website. They're currently out of stock on their certificates, but you can currently purchase biochar sequestration credits. In this case, they're guaranteeing the sequestration by burying the char deep in the soil. There is some debate still as to the fate of biochar in surface soils, in the aerobic active zones. It certainly has its benefits and is sequestering carbon, but it's when you bury it deep enough, you can guarantee that 100% sequestration versus, maybe we've got it for 100 years instead of 1,000, and that all factors into the value of the carbon credits. So in Minnesota here, we don't have a lot of rice husks, as we were talking about in the previous couple slides there. But in this case, wood waste is huge in Minnesota. The emerald ash borer, is devastating tons of communities' trees right now, and our wood waste generation is skyrocketing. Not only that, but we've got construction demolition type sources of clean wood waste that just need a beneficial home. A lot of those do get made into mulches and those types of things, but a mulch again is going to eventually degrade and enter the air as CO2 in a matter of dozens of years, whereas that the wood made into biochar is going to be in the soil for hundreds to thousands of years, possibly longer, depending on which research study you're looking at. And so this is from the Environmental Quality Board study from 2019 with a hierarchy of the best ways to manage all this wood waste. Biomass to energy in industrial boilers has been a conventional system used in St. Paul. There's a facility in Shakopee and one up in the Duluth area. There have been a number of other ones over time, and those are great outlets. But when that material is fully combusted into ash and all of the energy is utilized, then 99% of that carbon is going to the atmosphere versus 50% of the carbon being locked. And so that's kind of where the equations with biochar and energy get a little messy, because you have to burn about twice as much material to get the same energy generation as with a traditional biomass energy facility, but you're sequestering half of that carbon. So it's being able to make the economics work, that half of the energy is made up on that half of the carbon. And that's where it gets tricky with carbon credit markets and how much to sell biochar for. It gets messy in those ways because of the different values and how those different values get translated into dollars. And so the way that biochar in that process sequesters half this carbon is by changing the way that we look at the fire triangle. So if you go out in your backyard and you have a bonfire, you're going to add fuel, heat, and oxygen to start a chemical reaction that's going to give you, flames and heat coming off. So by changing the order that these happen in and really controlling with tight engineering parameters how much heat, how much oxygen, and how much fuel at what time, we can generate these very, very complex materials with all of these very specific properties. And it's the change in state of matter that is what the energy is driving, and where pyrolysis, this process of converting the wood into biochar, happens. So it's important to know that solids and liquids don't burn, only gases do. So if you have a puddle of gasoline and you throw a match into it, it actually won't light on fire unless you hold the match and light the fumes coming off. Everything needs to convert into a gas before it turns into plasma, which is fire. And so the process of fire actually has several different chemical reactions that occur to make fire happen. So say you have a lighter, you hit the lighter, it's butane gas that evaporates. It evaporates very easily at room temperature. So you're lighting that gas on fire, creating the heat then to drive pyrolysis. When you light a piece of wood or a piece of paper on fire, you're actually doing pyrolysis when you're doing that very simplistic process. And so the paper pyrolyzes, and then as it oxidizes and turns into CO2 and ash, that's where the most energy is gained. But by controlling that pyrolysis process and controlling the vapors in the right way, the energy equations work out such that you're carbon negative and you're creating this great sustainable product. Some of these reactions are self-sustaining or autothermal, which is the whole reason that a log continues to burn in your fireplace. It's an autothermal process. There's more energy coming out than what has to go in to keep it going. So there's energy to be had in these processes. And so again, the difference between charcoal and biochar is charcoal, we're going to keep a little bit more of the organic matter because we want to burn it again and have some of those flavor aspects. But biochar is going to be a little closer to the ash side, a little more depleted. So here's just another view of that complex series of reactions coming off the head of a match. You'll see here as the match turns into gases, and then eventually the gases burn, and you end up with oxidation byproducts. And you can see the same thing happening in my home biochar kiln to the right. You see the red hot coals are driving heat, which is in the areas that are exposed to air, oxidizing into the gray ash. And then where you see the black transitioning into the raw wood, that's pyrolysis happening. That's that pyrolysis zone. And so as I said, with the Victorians making their biochar, their charcoal way back when, really the only difference between a pile of wood turning into biochar versus being burnt up completely and oxidized is lighting it from the top rather than lighting it from the bottom. That's literally the most simplistic way you can make biochar, is by taking a pile of sticks and lighting it from the top instead of the bottom. It's very difficult to control that. It's very difficult to have it actually work. But if you have a little pit where you burn the material above and then let all the coals fall into a pit, that prevents oxygen getting from to the coals and is the second easiest way to make biochar. The third simplest way to make biochar in an autothermal pyrolysis system still is the TLUD process, which is top lit updraft. And this is the same principle that drives that pile or that pit method. You have biomass at the top that's being lit, and then as the flame front moves down, the burning of the material causes an anaerobic zone, and so that biochar accumulates. It has that heat to accumulate, but doesn't get burnt up into and oxidized because the oxygen is getting burnt up just before it gets there. This is one I built at home. It's kind of a cumbersome process. It's a batch process, and so you have to load and unload the thing in just the right way, and you have to light. It's kind of tough to light, so it's not the most practical approach. The more pragmatic approach that I came up with is this stack of bricks, essentially, where I'm actually making biochar in the part below using that flame front method by adding fuel faster than it's burning up. I'm creating a pile of coals that prevents oxygen from getting to the rest of the coals. And then at the end of that, I just shovel it into a wheelbarrow full of snow or water and quench it. And then by sieving out different fractions of it and washing off the fines, you can get some really interesting, I mean, literally charcoal. Or I utilize it for, I'll put some in my cat box. It's incredible for absorbing odors. If you have odors in your trash in your cat box, throw some biochar on top of it and you will never think about it again as far as odors. And then as I'm making that bulk biochar in the bottom, I'm actually able to also have a little grate above there where I take old soup cans and I put different materials into the soup cans to make specialty specific biochars. I've used expired cereal, expired chips, old socks, junk mail, anything you can fit in the can that's made of carbon is going to turn into biochar. You get a lot of different qualities based on what you use, though. Paper and those types of materials tend to generate a lot of ash, whereas wood and having more lignin content in the material helps to really bind things up, and having the existing structure more so just than like the paper lignin even too. So that kind of the next evolution above that, which a lot of the watershed type organizations are looking towards, is the Oregon kiln. It's a concept that was developed in Oregon. It's literally just a metal box. It's the same concept as a pit in the ground, but it's a metal box that you can dump out. And usually they're used for forestry cleanups, just to process material in a way that doesn't generate as much smoke. You'll generate no smoke if you feed these in the right way. You get a very efficient combustion of those gases coming off. So by utilizing an Oregon kiln instead of open burning these piles in the woods, they're able to, one, sequester carbon and improve the soils, but then two, reduce their exposure to smoke, reduce visibility hazards for other crews cutting it near them. Kind of another evolution onto that is, again, this flame cap principle, but now by adding a shroud around that Oregon kiln, essentially, you're driving hot air to come and create an air vortex. And so it's just a more efficient Oregon kiln, essentially, what these solo stoves and the Kontiki type biochar units are. The solo stove specifically is just meant to be a bonfire with no smoke. But if you feed that solo stove in the right way, you'll make biochar still. And then kind of another evolution of that air vortex concept is then the air curtain burner. It uses a forced air flame cap method to actively push all the smoke back into the fire. So it uses a diesel motor to drive a big fan, and usually these are just used to, just like the Oregon kiln, to reduce the visibility hazards and the visible pollution from burning wood, just a more efficient means of combustion. But if these are loaded in the right way, or in the case of the Tiger Cat, which is specifically designed with an auger system in the bottom and a cooling auger, that's an actual biochar machine based on this air burners concept, the Tiger Cat is. But by feeding it in the right way and making sure that everything's not turning to ash, like in the top picture on the right there, you see that there's tons of ash being generated. If they would go now and throw in a bunch of loose wood or some wood chips, that would help to quench out those coals and maintain the coals, and then they just need to extract the biochar out that door at whatever point. So kind of the next evolution onto that, which gets back to the soup cans that I use, is indirect pyrolysis. So this is where we start to get into the concepts that the big facilities are based around. And so a retort kiln is the most simple way you can build one of these. And all that is it's a vessel that holds the biomass that you want to turn into charcoal. So in this case, wood cut, firewood, and then they'll build a fire in the bottom underneath that material that wants to be made into biochar, and then it just heats it without allowing oxygen into it, and that's how the biochar is created. And so you'll see in the middle here, I have this temperature gauge, and what that is depending on the visual property of steel, you can estimate what temperature you're reaching. And so just based on the cans that I have there, I've estimated around 850 to 900 degrees, at least, that I'm achieving when making my biochar. And the reason that's important is you want to make sure that you're driving off different volatile compounds, that the potentially harmful compounds are being fully combusted. And that happens at around, you'll hear a lot of different numbers, but you want to get to at least 500, 600 degrees Celsius for 30 minutes is kind of the very bottom number. But you can make it all the way up to over 1,000 degrees, where then you come into some different properties with the material. Biochar now out of Colorado has an interesting approach. They have these big kettle kilns that are linked up in series, and then they are able to make these different batches of biochar, and they can use even contaminated wood, railroad ties, and painted and treated wood, because they're operating up around 1,200 degrees Celsius, which destroys just about anything. And then another kind of indirect process here, available for a fairly good price of $3,000 only, a kind of a shop heating or home heating biochar unit that just hit the market from High Plains Biochar. This uses kind of a cartridge. It's all made out of old kegs, and so they take the smaller keg and it fits inside of that bigger keg where you have the fire, and so that's just like the retort process. But in this, all the gases are still contained within your flame zone, and so all the gases will be getting burned up and used to drive the heat in this process. So you can make some kind of like my soup can method, very distinct batches of biochar. And then they also have an auto feed heater type of unit, runs 40,000. So it's a little out there as far as a price for something to heat with, but you can make biochar while heating your home with a commercially available unit, technically. This is what Jim will be talking a little more about, but this is what the city of Minneapolis is getting is RD-Char. It's an auger drive system, which means you have to have a relatively small feedstock. Definitely has to be wood chips. That's kind of the advantage of those air curtain burners is you can utilize full branches, full logs even, and not have to size reduce those prior to processing. The energy used to create wood chips can be a barrier sometimes here, but when you're in the cities here, the arborists are all chipping their wood anyway and trying to find somewhere to deliver that to. So when you're starting with chipped wood, RD is certainly a great approach. Out of Asia, you can get full-on energy production plants, shipping container biomass to energy plants. They're currently commercially available. I haven't seen one in person, but you can buy them. So it's not inaccessible. It's not some high in the sky crazy idea. People are doing this stuff, and they're commercially producing units in Asia. We just aren't buying them yet for some reason. FECO, they have an office out of Milwaukee. They've been experts in activated carbon equipment for decades. The activated carbon industry just is adding steam to the process of biochar or utilizing it for stuff like cement production. But these rotary kilns are the absolute most simple machines probably in the world. They're so simplistic. They function incredibly reliably. And this is what the activated carbon industry has used for decades and decades, and that's what some of the more successful actual biochar operations are utilizing is existing industrial equipment that's just repurposed to make biochar with. And it's all about capturing the energy, capturing the heat that kind of makes everything else, all the other equations work as far as the money. But so FECO, you can order these units today. They're available. Pacific Biochar goes into existing plants using this type of machinery, and they'll convert existing plants into biochar plants. Wonderchar out of Germany specifically purchases production activated carbon units that they convert into biochar units, and you can order those out of Texas. They're extremely affordable Wonderchars. So this stuff is available. It's just finding the right reason to buy it and the right justification to say that it all works. Glanris out of Mississippi and soon to have a facility in California. Very grateful to them as the sponsors of today's podcast or webinar. But you can currently buy biochar from them. David Bogue out of Roseville is a sales rep for them, and you can get a quote from him. You can get samples from him. Rice husk biochar available as we speak, and they use a rotary kiln process, which highly applicable to wood chips and other types of biomass as well. Just kind of a neat figure of Glanris showing that existing state of the harvested rice stalks getting burned or rotting, becoming atmospheric CO2. But when we take these materials, whether it be wood chips or rice stalks, make them into biochar, we're sequestering that carbon, and we can use it in all these incredibly useful ways. Glanris's biochar is already being used for drinking water treatment, for discharge water treatment, using asphalt and concrete. We already know we can do these things. We just kind of need to start doing them. kind of a lower tech version of the rice husk biochar. The most simplistic way for the average rice farmer or whatever to manage their material is to build a little indirect fire, have a little metal shroud, and then pile up the rice husks around that, and that heat then creates biochar without exposing it to too much oxygen. You'll still generate some ash, but it's not the worst thing in the world to have a little ash in the biochar, especially for soil applications. Rice husk specifically is very high in silica, which has there are currently operations in Asia that extract that silica for industrial applications. It's used in cosmetics, concrete, your desiccant packets that come in different electronics to capture moisture are made of silica. It has all kinds of industrial applications, and the rice husk biochar itself, certainly does as well. And then we start getting into these really large facilities where they have some of these vertical retort processes and really, really big stuff, which is promising. It's, they're doing that in Europe, and it's certainly stuff that can be done. But at a certain point, you start to hit an efficiency of bringing feedstock to a process versus bringing a process to a feedstock. The more that we can keep these at a manageable scale, that they're getting as close as possible to where different agricultural feedstocks or different forestry feedstocks are being generated, so that we're not trucking things too far and ruining all of our carbon benefits by trucking all of the feedstocks around. Getting back into Minnesota here, this is an article about the North Star Lime fertilizer production expansion program grant, where they're going to be turning corn stalks into biochar sometime this spring. The thing I like to point out in this particular article is that they say instead of burning the corn stalks, we're making them into biochar and then putting that back into the field to increase organic matter. So it's very important when we're talking about biochar to realize that there are different types of organic matter and different types of carbon. So soil organic matter is a term that's used when the carbon is available to microorganisms. And soil organic carbon is the total measure of that, including the stuff that's not available. So when we have a material like compost, it's very, very much that soil organic matter, the available carbon, and then biochar is very unavailable, and that's why it lasts for thousands of years. But because of that, like in the composting process, if you're trying to balance your carbon and nitrogen, you need to understand that biochar is not a carbon source in that that nutrient equation. And then this is also kind of my transition into peat. It's very easy to replace the use of peat moss with mixtures of biochar and compost. The reason that horticulturalists like to use peat is that it's very sterile, it's very stable. So it's very easy to know what you're getting and what its properties are going to be as a potting soil. Biochar is a little more questionable because it's so new, or new in certain senses, but it offers all those benefits of sterility, and the right kind of compost can be produced that's plenty sterile, produced in a high quality facility. Not all composts are equal, but mixing the right materials, we can completely replace peat moss. There's no reason that any application has to use peat moss. So let's keep that sequestered carbon in the ground, use biochar and compost made from actively respirating biomass, and knock it off with using peat. The UK has already realized this. They've said by 2024, no more use of specifically horticultural peat in England. So they're way ahead of us there. That's something we really need to get the US and Canada on board with, and there needs to be a reason for it, though. So we should be paying Canada for carbon credits to not harvest peat, pay Minnesota peatlands to not harvest it. That's the only way to drive it economically, but they should be leaving that stuff in the ground. And there's an important difference here between peat and muck soil. Harvesting peat is a very different process than wetland restorations, where sometimes peat soils do need to be excavated to restore water holding capacity in a wetland. or fix erosion issues from decades of tillage practices that might have caused a lot of runoff. So we do sometimes need to excavate soils that are technically peat, but muck salvage is a very different thing than peat mining. And so to the concept here of not all composts are created equal, it's very important when talking about compost to realize that it has to go through this biological process. If a material hasn't gone through this full decomposition process, it's going to have different forms of carbon that aren't what we're looking for in what's going to be called a compost. At different nutrient levels, different composts have different properties. So when the carbon and nitrogen is very high, it's a very woody material. That's where we think about stuff like wood chips, like raw wood chips. And why wood chips are not compost is because they're going to consume nutrients as they degrade in the soil. There's more carbon than nitrogen, so the nitrogen is all going to get eaten up, and so it's not going to fertilize the soil with nitrogen, but it's going to add that carbon that'll hold on to other nutrients and benefit the soil still. And that's also kind of where to think about biochar. And then at the other end, we have manures and biosolids type composts that are much higher in nitrogen, where those are going to be fertilizer materials, but they're riskier to plants. And so this is kind of horticulturally why compost is difficult, because it's such an active material, it's a changing material, and it can have less different results than expected if not considered properly. So that's why biochar and compost are such a great combo again, because the biochar helps to tie up some of those nutrients to buffer some of the activity and to make compost more stable and more predictable. And just when talking about compost, I mean, it's the Minnesota Compost Council hosting today's webinar. It's important that we remember that these aren't just composting councils; they're compost ingredients councils. Biochar is going to be an important ingredient in compost. Wood products of all kinds are ingredients in compost, and many of the compost producers also produce and vend those types of materials, and they're going to be essential to the biochar industry as well. There's really no separating compost and biochar when you start to think about where you're going to buy it, who's going to make it and sell it. Just again, back to that picture from the top, compost and biochar, that little overlap area is like peanut butter and chocolate. Compost and biochar just are the perfect combination. They have these great synergistic properties that make each one better, each one retaining nutrients and adding nutrients, and it's all great stuff. And we're currently moving to form a Minnesota Biochar Initiative organization. It'll be part of Minnesota Composting Council, the way that we're currently approaching it, but also considering the U.S. Biochar Initiative and U.S. Composting Council, and how all these different entities intertwine, and the synergies that all these organizations have as we think about how to move forward with biochar and compost and the combination of the two. So now to thank all our speakers and sponsors again here. Lanris, the Minnesota Composting Council, myself from Stantec, Jim with Minneapolis, and then Bridget and Brian with NRRI, and Kurt with the USDA. We did have a couple of questions that came in during people's registrations that I'll just address real quick. Is there a list of equipment manufacturers? As I kind of elaborated on in the slideshow there are a number of different sources of biochar equipment and carbonization equipment, a number of different existing things on the market, and a number of more specifically designed to biochar type machines. Cambium Carbon provides a really nice list of mobile equipment in their 2022 Emerald Ash Borer study that was for the Partnership on Waste to Energy, Hennepin, Ramsey, and Washington counties joint solid waste organization funded that study. And then, they're all different scales of equipment as well that we can construct. You can build a pit in your backyard, or you can buy a few $1 million worth of industrial equipment. There's a huge range of biochar equipment. How does biochar production compare to anaerobic digestion in terms of facility size and needs, energy production, and environmental benefits? Anaerobic digestion facilities are typically going to be larger, but there's really all kinds of different scales. As we got into with biochar, you can use a bulk shipping container, just those international bulk containers, the white chemical totes, and make one of those into an anaerobic digester unit. There are plans readily available online to do so. It all comes down to economies of scale when we're considering what an actual facility needs to be, but it can happen at all different scales, and your return on investment is all the equation and where that's coming down to. But biochar can also be used in anaerobic digestion as a catalyst, and the anaerobic digestion residuals can be made into biochar, specifically for PFAS concerns and biosolids from our wastewater plants. There are a huge number of projects that are looking at gasifying those wastewater residuals to make them into a biochar material and address those pollutant concerns. And biochar is going to sequester more carbon overall than anaerobic digestion, but there's a lot of different motivators. You're not going to make biochar out of wet material, and you're not going to do anaerobic digestion of a bunch of dry wood high in carbon. They have very separate feedstocks, and they've got synergistic benefits as well. Price points for different types of biochar, for what I've seen from the few kind of operational gasification units of the sewage sludge, about 150 a ton is usually what they're throwing around. But they have very different factors on the front end. They're not collecting a tip fee, they're just processing for a contaminant really, and this is a waste byproduct. So they're able to sell it for, they might give it away in many cases. Mixed quality from small scale production, so something that you might make with an air burner type unit, maybe around 300 a ton, and 500 a ton for anything commercially produced that's good quality. High grade sorted biochar is used for drinking water in place of activated carbon, or technically as activated carbon can range from 1,000 to 1,500, and activated carbon itself is typically going to go around 1,500 a ton. But all these prices are negotiable, especially when you're selling in bulk. If you have a bulk customer, that low quality stuff might be 100 a ton if they're taking it all off your hands. And most biochar actual businesses that are currently operating are making their money either off of tip fees and or carbon credits. And so then the actual selling of the biochar at that point is just kind of a bonus, but you do need to move the material to get the credits. So in some cases, they do need to move large quantities, but they also don't want to move them long distances, because then they're losing carbon credits. You have to track the material all the way from the point of generation to the point that it's buried in the ground to get your carbon credits. And then screening residuals, I assume from like wood chip sifting. That's great material, or residuals from compost sifting. Compostable products that are sifted out of compost can be made into biochar. It's a great use for those. They're a great source of energy in the biochar process. The thicker compostable plastics that take too long to break down in the composting process can be made into biochar. With the right system, the right level of engineering, you can do anything with anything, but it's what actually comes out as economical is always a balancing act. So we'll save questions for the panel time. I do see a couple coming in already. Yes, the slides will be made available, and yes, there'll be a recording available on the website here. But so I'll hand it off to Jim here next, and thanks for listening to me babble for 45 minutes. We're running a little long, but plenty of time for Jim here, and we'll dig into the panel.
All right, thanks, Nick. I appreciate that, and I do like the comparison of the chocolate and peanut butter. This is a good separate, better together. What I'm here to talk about is the Minneapolis program, the kind of named the whole program Cool Soils. from the aspect of what it does for the climate. Could you advance it there? There, thanks. What we're looking at in the city of Minneapolis, a lot of it is what we're looking to do is addressing climate change, and we have it in our both our climate action plan, in our 2040 plan, comprehensive plan, to use biochar to build climate resilience, as well as the, as you mentioned, the carbon negative component and what that means for building our carbon budget, building capacity back into our carbon budget. But with our climate actions, a lot of it today, to date, has been working on adaptation, and that's where our programs are looking at weatherization, a lot of efficiency, transportation issues, et cetera. Or that's a mitigation, I should say, but we're trying to figure out how to adjust to being at climate resilience hubs, what do we do with our change in the mix of trees that we have, and other issues on how to address climate change, and particularly on our most vulnerable residents who usually live in the BIPOC communities. And the other one where the other focus has been on is mitigation, which is avoiding or reducing greenhouse gas emissions, such as energy efficiency, transportation issues, going to electric vehicles, et cetera. But what's come through here in recent years, I should say in the past 2 years, is the understanding that avoiding and reducing GHG emissions isn't enough. We actually need to work on the concept of drawdown, which many of you may have heard, and going into the carbon negative or reducing the levels of greenhouse gases in the atmosphere to avoid the disaster that the Intergovernmental Panel on Climate Change is saying will happen. Please, next slide. And what we're going to be talking today, this is as of June, my new title here at the City of Minneapolis is Carbon Sequestration Program Manager. And it's kind of a big title, I did not make it up, but carbon sequestration, and Nick had mentioned that, biological is a great thing. Trees are very efficient collectors of carbon. And geologically, you've seen a lot of things such as formation of the limestone and other methods where it removes carbon dioxide from the atmosphere. The natural geologic processes tend to take very long periods of time, a lot longer time than we have. And then as Nick had mentioned here in the technical, where we had the large carbon capture machines and trying to change that form of that carbon and either pump it back into the ground, sequestering it geologically into such as reservoirs, et cetera, not the non-natural processes, or changing its chemical form, and so the introduction of carbon oxide, or calcium oxide. But what we're trying to do is, like I said, mentioned, is that the biologicals, trees are great collectors and storers of carbon. Next slide, please. So I mentioned is that they're great collectors of carbon. Why do we big machines when we've got it all over the place, very easy to use? However, if you take a look at the trees here, this is a street in Toledo, and please go to the next slide. That's the same tree, that's the same street 2 years later. And what happened here is that's emerald ash borer and what it comes through. The one thing about storing carbon in trees is that it's reversible. And storms, we had seen the tornadoes going through in Mississippi and Texas, what the devastation that it's doing, disease and invasive species such as the emerald ash borer, or before that, Dutch elm disease. And I do know how to spell invasive. Oh no, that's just something on my screen. Never mind. Development, where we tear down trees to put up new buildings, and that's happened a lot, particularly in the city, as we go vertical and taking up every square inch for a building. And climate stress is we're seeing the changes in the climate patterns. Minnesota, we're looking at not necessarily a lot warmer, but we're not getting as cold in the winter and a lot wetter. Or I should say the wetting is about the same, but it's more periods of intense rain or precipitation events with periods of drought in between. So it really puts a stress on the survivability of our trees and ends up totally, in total, coming up to the point that the carbon in the tree, as Nick had said, if it comes down, almost 100% of that within a few years is right back into the atmosphere. So it's part of the carbon cycle, but how do we stop that cycle or interrupt it and bank that carbon? Next slide, please. As mentioned, might have seen is that, emerald ash borer is coming through the Twin Cities right now. We in Minneapolis have taken out all of our public ash trees and have replaced them with the diverse species. So we've taken care of that, taken a look at a lot of the diversity issues that we learned from emerald ash borer and now, Dutch elm disease, now emerald ash borers. Unfortunately, there are about 998 million ash trees in Minnesota. We've got one of the highest density of our population's ash trees in the country. So we're going to have an outsized impact in Minnesota from this. And it's overwhelming the systems that are here for managing the tree waste. And that means that we're going to have a large pulse of carbon dioxide released into the atmosphere as we reverse the natural carbon storage units that we have. And in Minneapolis, St. Paul area right now, a lot of it goes to Dakota Energy. I'm sorry, not Dakota Energy, my pardon, but the St. Paul Energy Plant. And they're at capacity. There's only so much we can mulch and do other things. So we're looking at the return of large piles that potentially are burned or just allowed to rot, go back to the atmosphere, resulting in, they said that a big use of waste, and that is a big concern to the state pollution control agency and others, as you've seen with the Canby and Carbon working on the study with Hennepin County, Ramsey, and Washington counties. Next slide, please. So what we're looking at is biochar is a tool, and it's as Nick mentioned, it's a carbon negative solution. It takes the carbon, I don't call it carbon sequestration when it's going into the trees, more of a carbon storage, because there's a lot of chance that that carbon is going to be released within 100 years. And that's what the IPCC says we need to do to remove it for that period of time to have any effect on climate change. But they're great collectors, great stores, but what we're doing is banking. That is, Nick mentioned, that 50% of the carbon that we can change into a stable form. Now, biochar can be used as a beneficial soil amendment, and that's where we see the highest use of the material that we'll be making. However, it can be used for other things, particularly stormwater, filtration material, etc. And one of the neat things is that Nick had mentioned is that burying it deep. And actually, you don't have to bury it deep in order to get good carbon sequestration, but it's very dependent on the material you use and the temperature that you treat it at to get it in a sufficiently stable form where it can last for that period of time in those aerobic environments. And when we're mixing with compost to address soil health issues within the city, it's within that aerobic zone. So we have to be careful about what we do. So there's one thing about biochar is that there's biochars are different. There's don't think that, because it says biochar, it's the same. You have to use the right biochar for the right application. And it's mainly dependent upon feedstock, whether it's herbaceous materials like the corn stover or switchgrass, wood, or biosolids, as Nick had mentioned. And we find that wood is the best for carbon sequestration if you're looking at the long term. And there's some technical reasons in it. We'll talk about that. But the big thing is that all vegetation is made from three main components. That's cellulose, hemicellulose, and lignin. And the lignin content in wood is higher and the right type, where you need those it contains aromatic material. If you remember from your organic carbon classes or organic chemistry classes, and getting to that temperature where it breaks down or rearranges that lignin, the aromatics in the lignin, that's where you build that long-term stable biochar, and that has to reach a particular critical temperature, which Nick had mentioned is right around 600 degrees Celsius. And the big thing on it, if you produce biochar, what you're looking at, depending on the char, anywhere from 1.75 almost up to 3 times its weight in carbon dioxide equivalents. So if we get 1 ton of biochar, rough estimate is about 2.75 times that is what you're removing in carbon dioxide. So it's concentrated carbon, and proving that it's being stored and being done right, that's where we derive the carbon credits. Next slide, please. And this is just a cycle, won't stay on this one, talking about the atmospheric cycle and going through the ground collected by the trees and then released. And what we're doing with biochar just shows here is that through pyrolysis, you can create biochar, stabilize a large portion of that carbon that would otherwise be released, particularly the woody components. And you can also capture and reuse the energy as a means to offset carbon or fossil fuel emissions and do a further emissions reduction. Next slide, please. Our history has been, we've been working in biochar sphere in Minneapolis for about 12 years now. This will actually be the 12th year that we started working with it. And which is a pretty good, or not, I shouldn't say 12th, yeah, it's 10th year, my apologies. But it's an interesting study. We were one of the first cities in the United States to start looking at biochar in its use. And I meaning through the city, we ended up purchasing a large amount of biochar, about 650-degree Celsius wood biochar from Missouri, and I've been using that in demonstrations around the city. First discovered, or I encountered biochar in Afghanistan as part of an agribusiness development team trying to help rebuild at the agricultural base of southern Afghanistan in 2012. And when I came back to the city, took my experience to the city, and luckily it was some folks were very interested in it. Was able to get the char and start doing demonstrations and building relationships. I'm in the health department, so a lot of our initial work has been with urban agriculture in communities that are at risk, and particularly environmental justice communities and BIPOC communities. In 2014, we had started with a memorandum of understanding with the Shakopee Metawadaka and Sioux community, who is the largest composting facility in the state. So we've delivered the biochar there. We mix it with the compost and then deliver it to various agencies or places to use throughout the city. This is a short list. It's definitely not comprehensive, but some of the significant early work that we've done or work along the way. That's the Mishkiki Gitagon in the upper right corner picture, where you see the crop circles, and the other side, one side, that's the biochar side. The lighter side is not biochar. We're doing a comparison. We did see results in improved vitality, health of the material, and increased output. But that was one of the first starts, and that's a Native American inspired garden that's run by Ventura Village, the Indian Community Health Board, and Pillsbury United, as well as other local agencies. And what we're growing there is native seedlines, pre-contact seedlines. You're using the Three Sisters method, which is corn surrounded by squash and beans that go up the stalk, so help replenish the nitrogen. And we also did that with the Little Earth the following year in helping rebuild the community there and trying to address the health issues from adjusting to a Western diet and obesity, diabetes, and other issues, as well as helping restore cultural benefits. This is an offshoot, or very similar to a method that the Native American community in the Minnesota and the Dakotas used to help rebuild their carbon in their early agriculture. This is adapting and reusing what was culturally appropriate for them and growing culturally appropriate foods to address their health issues. In 2016, we're working with the Parks Board on a large-scale tree program, looking at 400 bare root trees planted with the biochar compost, various amendments to concentrations and controls to look at how biochar affects tree studies over a long period of time. That is still working ongoing. I have to get an update on where we're at currently with that study. 2017, we took the Chicago lot, which is that's the bottom picture, which has been a very good success story for us. It's a vacant lot. We working with Pillsbury United and 21st Street Urban Farming Coalition to plant this, and we built it from the ground up as a biochar garden. So everything there is grown in biochar and compost mixed together. It's been very successful, and we're using food packages from there to deliver to families with children impacted by lead poisoning in order to improve the nutritional base of the children and hopefully make them resilient to the uptake of more lead by reducing their iron deficiency. In 2019, Bloomberg Philanthropies found out we were working with biochar. Very surprised to see anybody in the United States working it with the degree that we had. So I ended up being able to go to Sweden to visit the Stockholm. They have a municipal biochar facility that they've been very successful, known globally for their program. And they're taking their wood waste, making biochar out of it and mixing it with compost and back to some of the residents, but also using it a lot in their city infrastructure, particularly their trees. And they've had fantastic success with that. And then along that, I don't have a picture here, but we, along with Hennepin County and MnDOT, Minneapolis, we tore up 4 blocks of median in Hiawatha Avenue, replaced with biochar compost and swale to increase infiltration, and then planted a pollinator lawn mix. So they're trying to recreate pollinator or create natural pollinator corridors to bring pollinators, native pollinators, up into the neighborhoods. We also planted about 40 trees with the compost biochar. So it's undergoing, and we also had a biochar resolution saying that the City of Minneapolis backs biochar as a means to combat climate change and supporting it, and that passed through City Council. 2020, we put it into our 2040 comprehensive plan to build resilient communities, climate resilient communities. In 2021, we received a grant along with Helsinki, Stockholm, and Boulder on a Carbon Neutral Cities Alliance grant to look at biochar and develop up game plans for cities to work with. And we worked with Cambium Carbon on that program, and that helped quite a bit. Marissa from Cambium Carbon was the agent we worked with, and then it was able to help her out with her production of the wood waste study that was done for Hennepin County, Washington County, and Ramsey County. In 2022, this is the biggest year we had, is that we received a grant from Bloomberg Philanthropies, one of 7 grants worldwide, only 3 in the United States, for the production of biochar. So that is why now I am the Carbon Sequestration Program Manager, and I'm actively trying to design in place a biochar manufacturing facility down by the university. And we also put biochar into our climate equity plan for rebuilding green space and turning the city assets into carbon sinks and addressing other climate mitigation and adaptation. Next picture or slide, please. Cool Soils, like I said, it's kind of a cheesy name, but it's trying to figure out some way to brand this, and it's a carbon negative approach. Nick had mentioned that biochar is carbon negative, but we use the gas that's coming off of volatilizing off the wood when it's heated externally to turn around and do the combustion outside of that retort, and in order to the biochar feeds itself. So it's using the volatiles off of there to drive the process, and it's a continuous process. The one thing we are looking at, the RD char was what we were originally looking at, but it looks like we'll likely be using a rotary kiln, similar to what Nick had stated on that. Continuous process using wood waste, primarily a lot of it from Xcel Energy line maintenance, and so under our green energy partnership with the city and the Centerpoint and Xcel Energy. We're doing pyrolysis, which is Nick had gone over. But it's a continuous pyrolysis. We'll talk about in the next slide what the uses are, but we've been using, from what we started, we've been working into a lot of different areas with biochar. And this is where I talk about not all biochars are the same. and it's really dependent on feedstock and temperature and also particle size. For the most part, most of our work, over 90% of our work has been with biochar and compost. And as Nick said, that the peanut butter and chocolate comparison, good separate, better together. And then we're also looking at developing carbon removal credits to help subsidize our biochar production. That's one of the economic drivers here. It's very, biochar is recognized as being very stable in the ground, depending on your production and the results of your chemistry when you're working with the verifiers. You don't need to have deep burial in order to approve it. It's you can get stable carbon for long periods of time in the soil, such as what you see in Terra Bretta in the aerobic zones. With our project, the goals are local production, which I'm currently working on. I hope to have a unit up, said late summer, early fall next year, ready for shakedown and starting with the production. Climate equity is our second goal. We're working with partners, the community partners in the green zones to provide biochar and assistance for them in order for the local partners to be able to develop their own solutions for their own communities. They know better than us. We're looking at ourselves as being on tap, not on top. And the third is to be a regional asset, to be able to provide biochar that's appropriate for the diverse needs to the metropolitan area. So that's long-term what we're doing. And by keeping things close, both our catchment area within the county or the local areas and our deliveries within the metropolitan area, we can still get the climate benefits without having to transport a long ways. And we do have to do a life cycle assessment to determine what is our footprint in determining what is actually being removed. And then once the biochar has been put into a system where it cannot be removed, such as mixing with compost or put in the ground, the tracking stops and it's counted. The main thing they want to do is make sure that the biochar is not used as a fuel source. Next slide, please. This is just a quick look at our current uses. Urban agriculture has been by far the largest use, but we are looking at, we've been doing work with urban forestry in the hope to enhance that across the way, as barewood stock is a very most cost-effective way to replace trees. And particularly, we have not had 90% of our ash trees are on private property, and they're going to need to be replaced, as well as all the other public trees across the metropolitan area. And if we've been working with our park board and the Hennepin County Forestry in order to look at biochar mixed with urban forests in order to decrease mortality and increase thrivability. Another major area where we see is transportation. We are currently working with Natural Resource Research Institute and other research agencies and MnDOT on developing the standards and specifications, as well as getting it on the approved materials list for MnDOT, which will open a lot of the transportation corridors. And we see that as one of the largest markets for government agencies in order to utilize large quantities of biochar, build increase ecosystem services along those corridors, and build carbon sinks. Landscaping, we've already incorporated it into 4 firehouses ourselves and are looking at meeting with landscapers for use in this in the wider broader area. And the third area we're getting into is with stormwater from both passive, such as the median you see in the lower left in infiltration, but also with filtering out material. And that, again, Bridget and Brian are more familiar with that on what it means. Depends on what contaminants you're trying to remove and what temperature and feedstock you need to have. In the future, we see doing more work, and Stantec has been working on some projects with surface water. We hope to partner with them and Public Works and other agencies to help not only do it ourselves, but create material that's suitable for that application. And that's another one we're working with various researchers on. And also exploring it in the use of as a replacement in the use of concrete and also asphalt, as well as remediation on brownfields and stabilizing contaminants. But again, it depends what you're looking at and how you're going to do it. Biochar by itself, it goes on the ground. There's one thing we didn't mention is why it's good for urban agriculture and forestry and soil health. Is biochar itself does things with nutrient exchange, cation exchange, etc. But it also interacts with the microbial community and microfungal community, or the mycorrhizal fungal community, in both as a electron acceptor and donor, in both as the way it goes there, and at higher temperature it shuttles electrons around. So it's kind of like an ATM for chemical reactions, and so you really see a lot of microbes building up in the area of it, and using that to restore the ability to service and help plants. That as we before with all the inputs we've done, we've really crippled the ability of our plants to making our soil sterile. So rebuilding soil health, aggregate formation, drainage, increased drainage, and the ability for the plants to thrive and build additional stable soil carbon as it does it. Next slide, please. As we mentioned, that this is for mitigation. This is recognized by the IPC as carbon negative and creates a carbon sink. So that's one of the areas where we're looking at it to actively reduce our carbon emission, net carbon emissions for the city, and as well as adaptation. We're looking to help build the drought resistance of our urban agricultural base, as well as our urban canopy, help reduce the heat island, and absorb excess stormwater. So we've had a big problem with flooding. If we can increase the infiltration through reducing bulk density and the ability to retain water within the biochar and surrounding soil to increase plant growth and evapotranspiration. And then finally, boost the tree canopy. Next slide, please. As I mentioned before, we did this study with the Carbon Neutral Cities Alliance with Boulder, Stockholm, and Helsinki. We came up with our application that is found. I can get the website out later on where you can find the final products for this work and what we did on it with Carbon Neutral Cities Alliance and Cambium Carbon. Next, and then biosolids. Helsinki was working on biosolids. These are some short list of the community partners that we have been working with, such as MnDOT, MPCA, and others. And we hope to expand this work out, this list out. This is not an inclusive list, but as we build, we've seen the knowledge of biochar increasing in recent years, and its adaptation and use. So we hope to be a resource, and that's been the big limiting factor. It hasn't been available, and finding the right char for the right purpose, otherwise you're not going to like your results. So that's another area we're working with the U of M and NRRI to help figure out. Next slide, please. And here's my contact information. Drop me an email, jim.doughton, and then you see Minneapolis work there. That's my personal cell. It's on me. If I can't answer you, send me a text or leave me a voicemail. Thanks, Nick.
Yeah, thanks very much, Jim. And apparently we're both a little long-winded. We're gonna need to practice our presentation.
Oh, sorry about that.
No, that was incredible information. You're doing so many things that I mean, you were talking pretty fast there to even cover all that. So it's it's incredible how far along we are, really.
All right, thanks, Nick.
So just some housekeeping stuff quick. Lauren, if you could launch those poll questions, we'll present some poll questions for everyone to answer. Specifically, if you're looking for continuing education credits, please answer the polls, but we would like answers from everyone on the polls, especially the opinion questions. And if you're just here for the credits, you can take off at this point. You've already achieved the continuing education credits, but I'll stay on till noon here, and we'll see if the panelists are able to as well. But we'll get through as many questions as possible in that time. And so the PowerPoint slides and a recording will be available following the webinar. You'll receive a summary email from Minnesota Compost Council. Where did data points for the price points on biochar per ton come from? Who publishes the price for biochar? As with any bulk type product, it's very rare to find an actual published price for any bulk quantities. Those are usually kind of on a deal basis. But as far as like small quantities, anything less than a cubic yard, you can find some. RDChar has prices on their website. But specifically for the $150 price for biosolids, I got that from a feasibility study for a wastewater plant. The 300 to 500 for commercial biochar is from quotes that I've received from out-of-state biochar producers. And then that 1,000 to 1,500 number is from a stormwater project, a quote that was received by another professional. Can you explain what you mean by biochar being added to anaerobic digestion as a catalyst? One of the great properties of biochar is that it has a very high internal surface area. So I'll go back here. Yeah, answer it. Oh. So we have to close the poll? Okay. Yeah, I guess whenever the poll's done, if Lauren could close that out. But so regarding anaerobic digestion, the high internal surface area, all of these tiny pores are what give biochar its great properties for being able to, one, absorb water. That's absorb with a B, means to pull in physically. It'll absorb water, and different microorganisms will populate all these pores. And then biochar also adsorbs with a D, adsorbs chemicals, which is a chemical bonding process where that's how nutrients and different pollutants are sequestered into the biochar. And so when it's added to anaerobic digestion, it provides this catalytic surface, this high surface area where the microorganisms are living and producing biogas, and it adds to it speeds up the gas generation essentially, and it also does similar things in soil and compost. Given the number of biochar initiatives in Minnesota, is there an effort to organize around the topic, such as an interest group or advocacy group? That's exactly what I'm trying to kick off with today's webinar, and what we'll continue developing moving into the June summit. But as I tried to get at with this slide, we'll be starting the Minnesota Biochar Initiative organization under the wing of Minnesota Composting Council as an existing 501c3, and we'll be exploring down the road whether MNBI becomes a separate organization, or if we rebrand the Compost Council into a broader organization, or what will all happen there. But we are actively working to establish exactly that type of organization to connect all these different efforts and make sure that we're not duplicating efforts. Will the system chosen by Minneapolis reach a high enough heat to process treated and painted wood, or will wood from arborists be the only input? Wondering how construction waste will factor into this system, if at all. And Jim, looks like that one's directed at you. You still there, Jim?
All right, that helps if I unmute myself.
Yeah.
Yeah, the construction material is a viable stream. However, it has to be untreated wood.
Yep, and it all comes down to the potential pollutants and what can be, certain things will remain in the biochar material, certain things will be emitted to the atmosphere. But as far as what can be used, clean wood, prevents us from having to worry about a lot of that stuff. And we have a huge number of sources of clean wood in Minnesota. So it's lowest hanging fruit, and it's the easiest, most reliable material to use.
And Nick, I don't know if you heard my points before about not using treated wood. Yeah, you have the clean wood, but one of the other major issues is that a lot of it has nails in it. So any processing that have to do it, unless you're using like the bulk, such as like the air curtain technologies, if you're looking at chipping the wood to make particles, is that you need something along your process line to handle the nails or the metal in there. And that's an additional cost and may not be in the capacity of the producer.
Yeah, and that's an important point about the process line. the different prices you'll see and the different quotes you can get on industrial equipment will generally only cover specifically the carbonization, the biochar production unit. But sometimes you're going to need to have a dryer for the feedstocks to get to the right moisture content. You might have other factors that come into play, chipping, grinding to get to the right size fraction. It's not just making the biochar in every case. So let's see, PM and other emissions from open burning of wood as a health concern. You mentioned certain biochar processes reduce emissions. Can you talk a little more about that? Which processes are most effective at reducing emissions? So when it comes to reducing emissions, there are a lot of different technology levels for biochar. There are full-blown gasification systems, which are gonna be capturing all of the gases that come off and recovering certain fractions for making aviation fuel, diesel fuel. That's when we're starting to talk about plastics. But by treating plastics in the right way and capturing the right fractions of those emissions, we're able to turn plastics back into usable plastics and usable fuels. And that's you can have any level from that down to an open pit in the ground where you're not capturing anything. You're just kind of having a bonfire, and much of that is being lost to the particulate matter and the emissions coming off of there. So I'll try to keep us moving now into the panel. Kurt Spokus with the USDA is on our panel here, and if you wouldn't mind to jump in here and talk about the slide that you prepared.
Sure. So my name is Kurt Spokus. I'm a research soil scientist with the USDA Agricultural Research Service. And for those of you that don't know, the ARS, or the Agricultural Research Service, is the in-house scientific research arm of the USDA. So our mission in the ARS is primarily focused on agricultural problems from the field to the table, which affects all Americans. Today, I was just going to give a very brief overview of some of the biochar research efforts within the ARS. We have an effort that's referred to as CharNet. This started back in about 2008. It is a multi-location effort across our entire agency. We have about 20 states involved in this right now, and we're looking at all different aspects of the biochar research dilemma. Here in St. Paul, I've primarily been looking at the mechanistic alterations of the greenhouse gas that Nick brought up a little bit in the slides, where there's been a lot of emphasis placed on the reduced N2O, or nitrogen dioxide emissions coming from the fertilizer from soils. The biochar has a way to interact with that, and I've been looking at the mechanisms behind that interaction. I've also been looking at all of the interactions with dissolved nitrogen species, other agrochemicals. In particular, for the last couple of years, I've been looking at the aging cycle in soils and looking at the various soil by climate environment factors. And here in Minnesota, we have some of the oldest biochar research plots that go back to about 2008, where we've been evaluating about 8 different biochars applied to the soils out there.
Yeah, just a great example of the incredible level of research that we're already at in our own backyard here in Minnesota. It seems crazy that we don't actually have a commercial producer at this point, but I'm sure it's very soon to come. And so I'll now introduce Brian Berry and Bridget Ulrich with Natural Resources Research Institute, NRRI. If you guys could each just give us a little bit of background on yourselves and what you're up to at NRRI.
Sure. Sorry that I'm not seeing, can you see me?
No, I don't believe so.
Huh.
So here, I'll close the poll out.
You don't need to see me as long as you can hear me, I suppose.
Yeah, yep.
I think Bridget had to jump off to another meeting.
I do. I have 5 minutes to just say hello to myself.
Oh, so. You go ahead then, Bridget. You go first.
Yeah, I'll just be real brief. So Brian and I are at the Natural Resources Research Institute, and we sort of tag team our biochar program there. So my group is focusing on the application development specifically for water treatment. And just the one point I want to make before signing off is that not all biochars work for all water treatment applications, and it's a bit more of a science behind it. So just if you're planning on using biochar for a water treatment application, make sure that the biochar you're using has been evaluated for that purpose. And I'll just pass it over to Brian there quickly. And thanks everybody. I'll need to jump off in 5 minutes. So.
Yeah, thanks for being with us, Bridget, and sorry for getting the timing a little extended here. But if you'd like to hear more from Bridget on biochar, the St. Anthony Falls Laboratory puts their webinar series up on YouTube, and she just spoke a couple weeks ago. Very great overview of what her work's been.
Thanks.
Yeah, hi. So my name's Brian Berry, and my background is in chemistry. And when it comes to biochar, really what that means is our group is taking advantage of our analytical chemistry experiences. So our group, we tend to try to find collaborators for projects where, you know, our group can be in charge of the biochar production and characterization and provide those materials with that information about the material to people that are going to be doing more application-based research. For example, Bridget, she might be doing absorption studies for environmental contaminants as an example. Additionally, another area that, you know, aspect of what we get involved with is trying to promote the economics side of biochar. So we team up with industrial collaborators, and we might do a demonstration project where we're trying to basically demonstrate the economics of a large deployment opportunity, you know, and those are kind of the projects I'm interested in, is where does the large deployment opportunities exist in our state, and how can I be involved in that? Just because I think, you know, if the ultimate goal is to move the dial on atmospheric carbon, then we need to be focused on large deployment opportunities. So yeah, I mean, I would say that, you know, one of the things to wrap up is for characterizations, one of the specialties we focus on is focusing on the porosity of the material. And so there's a lot of different ways to skin that cat, but I won't go into today, but we're trying to be at the front edge, the tip of the spear when it comes to using the best methods for those sorts of analyses, which are often not easy.
Yeah, thanks. And so we don't have any fresh questions yet in the chat here, but please feel free to ask any questions from the audience that you may have in the question bar. And I'll start off with a question here for Kurt specifically. You've been researching biochar since 2008. Why is it currently not widely available?
In terms of the product?
Yeah, from your perspective on being around the product for that long, why isn't it taken off?
So I mean, as you kind of highlighted, humans have been utilizing burnt residuals for their entire history. And the whole reason I think that's really limiting its overall large-scale jumps is the lack of fundamental understanding in the chemistry going on. We're still scratching our heads wondering what is the fundamental property that will predict a particular application. That to me is amazing when you look at the amount of history of research that has gone into this material and the fact that we're still debating about what properties go into the overall mechanisms that we're thinking or hypothesizing about.
Yeah, Brian, would you have anything to add there?
Not really. At the same time, I really, so I've been in here for about 4 years, and so I still consider myself somewhat green in the biochar area, but certainly would agree with Kurt. You know, his experience is pretty vast in this area. So.
Mm-hmm. Yeah, and it's a lot of times with these deployments of technology, there's a lot of growing pains with things too. A lot of failed attempts, a lot of tries that fail for business reasons, not even because of the technology, but that can set back some of these industries from gaining traction, from becoming more popular. And there are certainly risks involved with biochar. If you over apply biochar to fertile land, you'll actually remove available nutrients and potentially harm crops. You're achieving that sequestration of the nutrients, but you're doing it in a system where that's not the goal. So it's important to realize what we're trying to do, how we're trying to do it, and factoring in all these different variables is certainly the complicated part, but things we're starting to put the pieces together, I believe.
Yeah, I mean, I think the other thing I would emphasize is, on paper, a kiln seems like a simple concept, but in practice, that's not necessarily the case. And particularly if you want to make something that's amenable to a variety of different feedstocks, right? So it's not quite as simple, and I think that's a hurdle that still needs to be addressed for the biochar industry to grow.
Got a couple questions here. So contact information for the panel will be shared with everyone, including the recording and slides. How much do you know about how much biochar should be used per plant when growing on a farm, or per acre? So Kurt, would you have a general recommendation on tons per acre of biochar?
Unfortunately, we still don't have any type of guidance in terms of how much needs to be applied or should be applied. In general, it appears like the biochar performs better in land that is degraded or is lacking in fertility. Like you mentioned earlier about not applying it to productive land. Right now, we don't understand all the mechanisms behind its interaction, so we can't really optimize those types of applications yet. The co-application with compost is appearing to be a very robust methodology. So far, there hasn't been as many wrinkles in that rollout as there has been in direct soil applications.
Yeah, to elaborate on compost a little more too, one method is to combine finished compost with biochar, which has plenty of benefits in that approach. But the real bang for the buck is when we add biochar at the front end of composting and co-compost it. It has incredible ability to retain the nutrients that are lost to the leachate, to the, when it rains as we're aging compost, we lose a lot of the soluble nutrients, but the biochar has a huge ability to account for that.
Yep.
Is there a lab where we can send soil samples to determine how much char should be applied? I have heard 500 pounds to 10 tons per acre. And I've seen around 2 tons per acre, but I've seen numbers all over the board. But yeah, Kurt, could you touch on the testing that you have available, and then I guess Brian maybe also touch on whether people can actually send you samples, or what that process would ever look like.
Yeah, that'd probably be more a question for Brian, since we're not set up to really be a contract laboratory. We're mainly just the research portion.
Sure. Yeah. I mean, there was 2 parts to this question. Can you remember the first part?
Is there a lab where we can send soil samples to determine how much char to apply?
Oh, so you want to analyze, the question is analyze the soil to then determine how much biochar?
Yes.
I'm not aware of any sort of soil analysis that will then result in a prescription for a biochar amount. So
right, and in most cases with a soil analysis, you're not going to get that kind of exact prescription, especially with biochar being having so many unknowns, and also needing to factor in the properties of the biochar itself. Working with an agronomist who is knowledgeable on biochar would definitely be the way to actually implement it in your agricultural setting.
Yeah.
You know, making sure that your agronomist agrees with what you're attempting and using it on degraded lands and low risk areas is definitely the most potential benefit and the least risk in the situation.
So we did a recent soil amendment to a coal ash landfill cap out at Boswell, and we did 4 tons per acre, and we tried to get it, you know, we tried to till it in about 8 inches deep. And that was driven by literature, and we were aiming to get between the 3 and 6% by volume in soil. So that typically seems to be what most studies are at, but I've, you know, of course, I've seen some where there's less and some that are up to 10%.
And degraded mine soils are one of the most promising areas to utilize biochar, especially in northern Minnesota, where all, you know, our mines are all surrounded by forests, and forests that need to have some, you know, level of maintenance to avoid accumulating huge amounts of fuel. So there's huge opportunities to just utilize it even for mine restorations.
And then as far as analysis goes for, you know, this is certainly probably something that people would need to ask me outside of this, because it's not a simple question, but there are a couple places I would recommend. Most people that analyze biochar tend to start off with proximate and ultimate analysis. And for that, I would recommend a company called Timber Products Inspection, or TPI. In fact, a Duluth resident is the one who started that company. It's a subsidiary of Bell Labs, BEL. So it's TPI, but it's under Bell Laboratories, which is out of Georgia. So that's my recommendation for proximate and ultimate. There's another lab out of California that I've never worked with called Control Labs, that specializes in some biochar characterization, but I couldn't speak to, I'm not familiar enough to recommend them. When it comes to our lab, you know, we're a research center and we're publicly funded, so we're not allowed to compete with, you know, private labs as far as cost goes. And then furthermore, you know, we're doing a lot of things besides just biochar characterization. So we typically tend to take on clients that have a minimum amount of work. Like, so you probably need a minimum of 10 different samples for our lab to be interested in getting involved. Otherwise, it's just not worth our time. But anyways, yeah, we do that though. Just to be clear, we do non-research related biochar analyses for external clients. But it's just something.
Even for like a single soil sample, the U of M Soils Lab in the Twin Cities here is a great resource. They're fairly reasonable on what they charge for a general fertility test. And
and we don't.
What you actually need for a biochar test isn't even very well determined yet.
Yeah, and to be clear, we don't. We just analyze the biochar material itself. We don't do the soils. So.
Yeah, so that kind of relates into this next question here. Is there a minimum biochar particle size that limits its attributes? And I guess just at a quick high level, I would say certainly not. They're at, you know, desirable attributes at every particle size and application, huge numbers of applications, but that's really specifically your research, Brian.
So I mean, particle size, typical particle sizes don't even approach the let's say the impactful pore sizes that biochar can offer. I would say that, you know, a lot of that has to do with soil mobility, right? Like, how does the biochar migrate within the soil? And if you're using it in a soil amendment, particle size could be important there. But honestly, I can't confidently answer that question. I'll refrain from trying to make any assertions about particle size and property or performance properties.
Yeah, I guess it's much more the pore sizes and the pore structures that are more finite stuff you look into.
Yeah, I mean, assuming it does, like the biochar doesn't migrate, and my instinct would be that particle size is not as critical as other attributes.
Okay. We have a recommendation here that Control Labs is an excellent lab to use, and they'll do the International Biochar Institute standard analysis as well as proximate. Whoever input that one says they used it for their IBI certification. And so that quality control and certification of products will be a whole mess of stuff we'll approach down the road here. MnDOT currently has a project, which Brian, you're on that one, looking to set quality standards for use of biochar and stormwater applications. So could you elaborate on what MnDOT's looking to do as far as setting standards?
Yeah, so this project, they're looking for specifications for implementing biochar as a component of an engineered soil used in roadside swales and conveyances. So basically what we're going to be doing for the Minnesota Department of Transportation is looking at viable feedstocks within the state, viable pyrolysis production mechanisms, right? So we'll try to mimic what will be available at scale, and then to develop some tests that will qualify the biochar material as a functioning material. So one is we're going to check mark that we're doing no harm, right? So you need to verify that you're not introducing anything harmful to the soils. And then second, make sure that it has performance properties that will actually allow it to function. You know, a lot of the stuff for that particular project has to do with soil compaction and hydraulic conductivity as much as it does absorption. But yeah, that's essentially what we hope to at the end, is that we can have a set of guidelines to make sure that the state of Minnesota is putting in something that's functional and is also not detrimental to the environment.
Yeah, and they're you know, from MnDOT to watershed districts, all these stormwater features all over the state. We have a huge amount of stormwater that gets treated every year, and we just need to start making the biochar to put in the projects. I started out doing a lot of drainage engineering in my early career, and that's actually how I kind of came into biochar, was wanting to use it on stormwater projects but not having it available. And now here trying to just to get it made still, but pretty soon we'll have it available, I think. On the agricultural side, I guess that's another big area is manure storage and the ability of denitrification during manure storage, preventing the release of nitrous oxide and methane, and then incorporating that, you know, that's then incorporating that biochar into the manure at the same time also. And as far as like USDA funding for biochar application, there are some sources out there. It's not even touching on that manure storage topic yet. But Kurt, could you talk a little bit about Code 336 and the NRCS stuff?
Yeah, I mean, so there's a lot of various requests for proposals that are looking at all varieties of biochar products out there. Within ARS, we're also looking at it in terms of a feed additive, looking at it adding in the front end versus an application at the end. We're trying to balance all of those necessary nutritional requirements and seeing what actually is going on with the digestion within the animal. We're looking at a lot of that through in vitro studies. So we're still at the beginning phases of those research efforts. There's other university partners involved in this, and unfortunately, I'm no longer able to keep on top of all of the biochar research items out there. But there's a lot going on at the University of Nebraska in terms of the feed trials, and the storage. I think it's Oklahoma, and I think University of Florida has a couple of projects funded on that side of it as well. So there's a lot of work ongoing, and hopefully we'll understand more of the mechanisms out of the results of those studies.
Mhm. Got another question here. Using biochar as a landscape mulch instead of wood chips. Seems like it might be a good use, except for the color black, which could lead to heating and plant injury in sunny locations. So I've got a few things to say about that actually. That heating property, I've actually used some biochar this winter as a snow melt. You know, rather than using salt when it's too cold, salt provides you no traction. It's only a chemical melting agent. Below certain temperatures, it doesn't do anything, and there's no reason to apply salt. Biochar gives you the advantage of the short-term traction. Some people are worried about it tracking fines into your house. I observed none of that. All the fines clung to the ice. And I also used a sorted fraction, which didn't have the fines in there. But I've also noticed that it does absorbs heat, and the area, my path where I had the biochar melted much more quickly than the portions where I didn't have biochar. Specifically for that surface application as a mulch, there are some studies that have shown that it's great at repelling slugs. Much of, like, as far as soil science goes, studying the surface is very difficult, as Kurt can touch on further, but it's very difficult to study the surface, and there are tons of surface uses and surface benefits that could be realized as well. Yeah, Kurt, would you elaborate any further there as far as any harm to plants that might occur from heating of the soil and how biochar could affect that?
Yeah, I mean, there is some concern about the changing of the soil albedo, or the absorption of solar radiation by the soil due to the black color. That is a genuine research question that needs to be looked at and examined. We have seen it in our field plots out at Rosemont, that the snow is first off of the biochar amended plots, just because that they do absorb more solar energy from the sun. So I could envision situations where that would be a detriment for plant growth. The added benefit that the char does have is the alteration in the whole hydrologic cycle and reducing evapotranspiration losses. So that could be offset some of those heating benefits. I'm not an expert in that whole balancing of which is a positive negative in that whole arena.
And the other kind of aspect that factors in there is thermally treated wood, which is a very promising product. There are different types of thermally treated wood that are used for everything from siding to any application for wood. Some of those are charred on the outside for appearance. And I guess, Brian, would you have anything further on thermally treated wood? Oh, you're muted.
Sorry. In what context would you like thermally treated wood? What application are you thinking about?
Just its applicability for housing exteriors and longevity for outdoor applications.
So we have a colleague of mine, Matt Arrow, that's kind of been his focus of research for a long time. So just to be clear, thermally modified timber, I would say, is completely different than pyrolyzed material. Like you at the temperatures they thermally modify wood, you're not really the onset of the dehydration reactions that ultimately end up in the graphitization of the material are not occurring at those temperatures. So, but I do know that there are increased, don't quote me on this, it's either fungicidal or termiticidal resistance, or maybe both, I can't remember, benefits from doing that. I know aesthetically, one of the issues that some people have with TMT is that it turns gray in a short amount of time. Some people like that, but I think that's the hang up for the industry adopting TMT as a large scale product. Although, again, Matt Arrow would be the one to talk about this. I know Forest Products Labs out of Madison, and then Matt Arrow up here at NRRI are really kind of leaders in that area.
Yeah, and then just keep back here to the thinking about it as a surface mulch. Yeah, it's all about what your landscaping goals are. If you like the way that biochar looks, by all means, it'd be a great surface mulch. you're going to lose the black color eventually, but I'd imagine it'd hold that color for quite a long time too, just more dependent on if it gets silted over or any kind of deposition on top of it. So interesting idea. I've also seen folks using biochar mixed with epoxy resin for countertops and floors. There are uses of it on foundations for insulation mixed with grout and then applied to foundations to further insulate. Really, there's just such a huge range of benefits, and it's just a matter of being able to produce it at the right scale that it comes out economical. And it always comes back to the almighty dollar. Let's see. We've managed to fill a good chunk of time here, so we can probably wind it down. Do you guys have anything additional to add? No?
Nope.
Yeah, well, thanks for joining us today. Again, the webinar here is recorded and will be available on the Compost Council website. We'll send a summary email with contact information, and all of us are probably too happy to talk about biochar. It consumes too much of my time, I know, and I'm sure you guys do, but we're insufferable, and ask us questions about biochar, and keep your eyes out for information on the Minnesota Biochar Initiative. We are actively working on that organization, and we'll have a website which the video from this will be posted to, and that'll be kind of the first step in that direction. And mark your calendars for June 28th, the Minnesota Biochar Summit. It'll be at Coffin Memorial Union in Minneapolis, and should be an incredible time. It's going to be very, very information packed, very difficult to even select the agenda for that one. So be sure to attend that and continue looking into biochar. And if anybody's looking at large scale biochar production facilities or application projects, if you're looking for grant funding, we can certainly talk about all those topics if you reach out to myself or anyone on the call here. So yeah, again, thanks for coming, and thanks to our sponsors and our presenters here. We'll call it a day there. So thanks, everybody.
Thanks a lot.
Thanks.